Okay, so let's continue our RTOS lecture, and we're going to focus on multitasking again. We're going to sort of talk about what we talked last time in slightly different ways again. We talk a little bit more about context switching and preemption as well. So again, so effectively what your operating system is doing is to multitask a whole bunch of different computational threads. So the idea is that well, since we have a conventional processor, right, think of a single core processor, you can only execute a single task at a time. But the idea is that for each of those different tasks, it appears to each of those as if they have full access to that core, as if nothing else is running. It's like task 1 thinks it is have full access to that core and nothing else is going on. So that's of course just an appearance, but the idea is that this operating system is going to rapidly switch between all those computational threads and effectively thereby sequentially executing indeed all those tasks but interwoven. So that's what is happening. So let's think about another example, this one for example. So the scheduler here is the part of the OS kernel responsible for deciding which task is going to run when. And the scheduling policy is like the algorithm, for example, round robin or things like that, that helps that is used by the scheduler to decide, which task is executing next. So if this diagram, I will switch back and forth a little bit because the next slide explains that. So first of all, in 1 we see that task 1 is executing. Then in 2 the kernel suspends, so it swaps out this task 1, so the kernel is forcing task 1 to stop because another task needs to come in, so that will be task 2. So task 2 is resumed in moment 3, and say while task 2 is executing, it locks a processor peripheral, for example, for its own exclusive access. So that happens in 4. And the kernel suspends again task 2 at moment 5. And at moment 6 resumes, say, task 3. But task 3 tries to access that peripheral that is effectively locked by task 2 and cannot do that. And as a result, task 3 suspends itself at 7 because it cannot make any progress. And that means that in this round robin fashion, task 1 is executing again at 8. That's what the kernel is doing. It resumes task 1. And then at 9 we'll see that task 2 is executing, and it finishes its processing, releases the peripheral, so that in 10 task 3 can actually execute and uses that peripheral. So this is like a flow of computation that can happen, and it sort of hopefully visualizes somewhat how the locking of a peripheral to a process may actually affect, in this case, the computation time of another task because it has to wait. So on the next slide, it's just all written out, and you can look at it when you download the copy. So what's happening at a context switch? Well, we first need to understand what's an execution context, because we talk about a context here, right? So effectively the execution context is all of this. Remember, we have a program counter, for example, which is pointing at the instruction that you will be executing. There is a status register. There are general purpose registers all the way to 32 of those. There's a stack pointer that indicates, because the stack is used to put, say, also say context, like if you write a program and you have a function call, then the function effectively tells the program to jump to a new address where the procedure or the function is coded up. So that means that you would like to store the return address. Where do I need to return back to? Like the program counter should go back to that program, to that return address, to execute the next instruction, which is after the function call something else. So then you would like, but the function call itself is going to have some arguments, some inputs. So you would like to write those on the stack. You would like to write, so then you created context, you have a return variable, and so forth. And so when you jump out of the program, so when you finish up, you can actually read what's on top of the stack, which is that function environment, if you will, and you sort of go back to the original, well, not the original, but you go back to where the program counter should resume the main program. And since you have nested functions, that's why you have a stack that can have many of those blurbs on there. And that's also how you can then think about buffer overflow attacks. Like I could say, if I have a buffer that I allocate of a certain size, and I ask in the function call for an input on that, I can potentially write too much in there if there's no boundary checking on that buffer, and I can override part of the stack, including these types of return addresses. And that return address can then be pointed at by you to another point in the program, for example, back into the buffer itself, because you have created not just a plain input for that buffer, you created some malicious code. So then you start to jump back to that part, and you start executing the buffer code, and then you have your access. So that's the traditional buffer flow attack. But anyway, I'm digressing a little bit. But the point is that you know, this is the execution context, and if you want to context switch out a task, then we need to remember what this was, because you want to go back to the exact same state as in the processor as where we left off. So that's context switching. So it's essential that upon resumption from a suspended state, a task has a context identical to that immediately prior to its suspension. So that's so take this example here. Say that the task gets suspended as it is about to execute an add. So this is assembly, right? Because you know, effectively all your I hope you remember, but all your C code is compiled, linked in libraries and all that. It's compiled into say an assembly code. Actually, if you open up in your editor and you just look at the say if the actual binaries, you will see all the assembly code appearing, and you can interpret it. So anyway, the point is that these are of course not written like that in the program memory, right? This is also translated into some number, right? So hexadecimal number, and and how that is translated depends on the actual processor. So the processor itself is different from one processor to the other, but they have the same kind of instruction set, like these loads, for example, and the additions or jumps or all that kind of stuff. That's a certain instruction set, and one processor codes up the instruction set with this hexadecimal notation, the other one with that, and they have their own wiring, but effectively the assembly is what you execute at the lowest level. That's how you can think about that. Alright, so the task gets suspended, and it is about to execute this add instruction, and the previous instructions have already set the registers used, like these ones, but like I've loaded in register 1 and register 2 specific values. They're here, like FA and E2. And yeah, now we have a context switch. So what you want is that when the task is resumed, the add instruction will be the first instruction to execute, and the task will not know if a different task modified register 1 or register 2 in the interim. Now, I'd like to take a quick step back. So this is about real-time operating systems. This is about context switching in real-time operating systems, where you can do that pretty much at any cycle. But the point is that take, for example, in the C code, an instruction that looks like A becomes A plus B. Then you have to load those two values. You need to do the addition, and then you need to write, and then you need to store that particular result into something else, for example. So usually you have 4 cycles. So we're thinking about instructions as units of 4 compute cycles. And when you do an interrupt service routine, that type of interrupt will let you finish the instruction that you see in the C code. Now here we talk about assembly though, so it's a finer level. But anyway, small detail. But the point is that I need to remember all of this context. So the process of saving the context of a task being suspended and restoring the context of the next task that you want to resume is called context switching. So that's what we are talking about here. So a context switch, when the interrupted task is suspended without the task suspending itself voluntarily, which we have seen in the previous timeline in the example that happened at some point. But if it's not done voluntarily, then we call that a preemptive context switch, because the scheduler or the kernel tells the task, nope, I know you would love to keep on going, but nope, that's not fair. I'll stop you because another task now gets its own chance to go ahead. So, for example, FreeRTOS implements context switching in timer 1 ISR. So, if you will be having a lab, an assignment, that have 2 parts. One is playing with some scheduling strategies at a very basic level, and the other one is just trying to get the FreeRTOS to work on your system. But in order to make that happen, you will need to have timer 1 available for the FreeRTOS. So, because the scheduler is being interrupted by using that timer, hardware interrupts, to do the preemptive context switches that need to be done. So that's how that works. Alright, so upon a context switch, the interrupt service routine here effectively interrupts one task but returns to another. That's effectively what happens. Of course, the interrupt service routine is just doing something like this. Increment the tick count. If the tech increment actually readied a task, so the task is finished, right? Then switch the execution context to if the tick is incremented to that of a task that is ready to be executed, right? Then, so that the task is first ready and it's also time to be executed according to the scheduling policy. If both are indeed true, then switch the execution context to the ready task, the one that is ready. And then return from the ISR. Now, this is of course implemented but it's not that straightforward. As we said, context switching takes some effort. You need to store everything properly. You need to recall that. You need to have the right data structure to put it all in. But effectively, that's what it is, though. And of course, you need to implement your policy. That's also important. All right. So this is, say, a timeline where you have some tick. Say ISR is coming in over here, and in this particular case, you have 2 tasks, say, and this one starts executing over here when you return from the ISR. So in the meantime, this is happening. You want that to be very fast and efficient, because otherwise you have too much performance overhead. So you would like that to be very efficient, and especially for real-time systems. I mean, it's really crucial. Of course, in any system it's crucial, but say if I have a human-computer interface type of application, we humans do not worry about a millisecond, right? So, that's kind of different. But if I have a compute-intensive task, then sometimes I would like it to be run uninterruptedly on my machine, say some standalone machine, without anything else to interrupt that thing, right? Because I like to finish it as fast as possible. But with the real-time system, you often need to do all those tasks under real deadlines. Take a car, right? So yeah, you need to, that sensor data needs to be checked. You cannot wait with that. And if your context switching is taking too much time, that makes your car more, say somewhat more unreliable. So you need to do good programming there. So let's talk then about scheduling policies. Yeah, that's the part of the scheduler that is also very important. Your RTOS, say FreeRTOS, wants to offer you, flexibility in how, you would like to assign policies for different tasks. So we talked about round-robin scheduling, but we'll do that quickly again, I think. Rate monotonic scheduling, and we talk about those, and then we'll go to these dynamic scheduling schemes. So a round-robin scheduling scheme is static in the sense that it just assigns these time slices to each process in equal proportions and in circular order. Here we see an example. And here we see, the arrival time and the burst time. So you have arrival times, you have a certain amount of time that it needs to compute. Well, say, all processes are handled without priority, you do it in circular order. So this guy, takes one step, then this guy 2, then this guy 4, then this guy 6 steps, then this guy is going to, and say, that your time slices are, limited to a few, to say 3. Sorry, I skipped something. Just a moment. The time slices are 3. So here I only need to work for 1, from 1/3 of my time slice, so I can finish. Here for 2, I can finish. Here I have 4, so I can only do 3 units of computation. Then I have to wait till everything is done and I can restart. This guy is now next, can do 3 out of its 6 units of work that it needs to do. Then we have this guy, it can only do 3 again, right? But 5 still needs to be done. Then the arrival time of this one is at 11, so it's before this one ends, so it waits a little bit. Can also do 3 units of work. 3 units of work over here, and then we see only 2 units of work, so you can even finish, and then 1 unit of work you can finish. Then you go all the way back. Well, these are already finished. You go back to task 3. Only needs to do 1 unit of work. This one needs to do another 3 units of work. This needs to do another 5 units of work, so it can only do 3, and needs to do the other 2 at a later moment. We have this one, it's also 8, so it can again only do 3 and the other 2 at a later moment. This one can finish because it only has only 3 units left, and that fits a single time slice. And here we have only 1 unit left, so that's done. And then the other 2 tasks can finally finish. So that's a round-robin scheduling. So that is static, it's preset, cannot change while it is executing. So about rate monotonic scheduling. So again, you assign, in this case, static priorities to the processes on the basis of the cycle duration of the job. So, the shorter the cycle duration is, so for example I have a task that needs to be called, say, every 1 whatever, say 10 milliseconds or something like that, and you have another task that is executing every 20 milliseconds, then you would prefer to finish the one with the 10 milliseconds faster. So this rate monotonic scheduling is generally preemptive because you need to kick out the other process in order to take over. Like the ones with high priority can go first, and those are the ones with the shorter cycle duration. So preemption takes place when a high priority task needs to be run, whilst lower priority task is running. So you get that done. So here's a picture. So say we have a period of 4, 8, and 12. So we go from high to lower priority. Alright, let's start the execution. This computation time is 1, here we have 2, here we have 3. So every 12 time units, you need to execute 3 time units. That's what this means. So let's see. So you start with this one, it's the highest priority. So I execute one time segment, say. Then this one is next because that's the next priority, and this one does not need to execute, right? It only needs to start executing at this particular moment, so it does not need to be. It suspends itself. It's finished. This guy is going to execute. Takes 2 time slices. This one is now next. It starts to execute. Oops, this one is ready. It's also its moment to execute, and it is high priority. Think about that ISR that we discussed just a little bit earlier. That fits all the conditions. So we have a context switch where task 3's context is stored and task 1's context is coming back in. So there it is. It executes. Luckily task 2 does not need to execute because it only needs to execute after this moment. So that means that task 3 can finish. And here we see the sequence of computation. Then there is an idle time slot because no one needs to execute. Nobody is ready for doing that. But then it starts all over again. We see that this one is ready. Then this one again. No one is still ready. There's an empty time slot. At this moment, both task 3 and task 1 is ready, but task 1 is high priority, so task 1 starts. Task 3 can finish completely. Task 1 again, and you can just keep on going. You see a repetitive structure appearing, by the way. That's always happening. And you see that this is kind of the structure of computation, how these different tasks are interwoven together. And yeah, you notice that these bursts over here seem, in this particular case, to be very regular. Indeed, every 8 periods. Also here, every 4. But this one is a little bit weird. It's a little bit more fragmented. Like this takes a bit longer and is in the middle of this period, is a bit earlier in the period, a bit in the middle, a bit earlier, and so forth. So you see these kinds of structures appearing, and that is like what we talked about earlier about that fuzziness. You don't exactly know, unless you do run it in a simulator, when these tasks are exactly starting and finishing and being interrupted. Okay. So deadline monotonic scheduling, what's this? Well, deadline monotonic priority assignment is a priority assignment policy used with fixed priority preemptive scheduling. So here the tasks are assigned priorities according to their deadline. So I have to finish at that particular future moment. That's really that's crucial. It's like a maybe a safety violation. It's maybe not that strict, but effectively your application wants to make all the deadlines. In other words, what are you going to do? The task with the shortest deadline, so the deadline that comes first in the future, is going to be assigned the highest priority because you want to finish that first. Boom. It's like a greedy approach. You first do that, boom, it's finished. And then the next deadline, you work for the next deadline in the future, and then for the next deadline in the future. That's what you do. So that's what we call deadline monotonic scheduling. And this one, if you have an example for this one too, is kind of an interesting one, is the shortest remaining time first scheduling method, and that's preemptive. So here, the process with the smallest amount of time remaining until completion is selected to execute. That's kind of different. It's not what we just talked about, the deadlines, but there's a certain amount of work that still needs to be done. And what do I choose? I choose the process with the smallest amount of time remaining until completion. So that's what we call shortest remaining time first. So here we have this whole list again. At time 0 we only need to look at those that have arrived, which are task 1 to 5, and say these are the burst times. So clearly this one completes first. I mean the shortest remaining time first. So you just finish this, boom, boom, boom. At some point, let's see where we are. We have here the 5, it finishes, but now a new task comes in. So P5, task 5, is starting out, can do only 1 unit of work, because now at moment 16 all these tasks come in, but notice they have shorter amounts of time than the remaining time, which is 5. So that's why we see here 1, 2, 3, 4. They all get executed before this one can resume, which happens right here. But again, it gets preemptively locked out, right? Context switched out, because at moment 27 we see here 1, 2 and 3 coming in, and there is still 4 left, and so we see 1, 2 and 3 coming in, and then this one can finally finish. That also shows you the drawback of this method, right? Because this one somehow got pushed out as that one task that is just unlucky. All the others got finished, but this one task got really unlucky, and you may not want to do that, of course. So again, it all depends on how you want to schedule your stuff. So now we talk about dynamic scheduling. So we talked about the deadline. Sorry a minute, didn't I talk about that before? Just a moment. Okay, so here, I have to read up on this a little bit more. So let's talk about earliest deadline first, which is sort of what I had in my mind when I explained the scheduling policy earlier.